Good day, ladies and gentlemen. This is Razavi, Assistant Professor of Faculty of Engineering at University of Science and Culture. The title of my presentation is Numerical Study on an Innovative Elastomeric-Steel Cushion Damper. My co-authors in this paper are Milad Ehteshami, graduate of Structural Engineering from University of Science and Culture, Dr. Mohammad Yekrangnia, Assistant Professor of University of Sheikh Razavi, and Dr. Alireza, Khaloo, Professor of University of Sharif. The contents of this presentation include introduction to dampers, introduction of elastomeric-steel cushion damper, cyclic assessment of elastomeric-steel cushion damper, and finally the conclusions. Introduction to dampers. In this slide, I am going to make a quick review on the history of development of some of the dampers. In 1972, Takeda et al. Tried to improve the post-buckling behavior of edge section braces by encasing the steel section in reinforced concrete. This method resulted in restraining the buckling of the brace and exhibiting full fine hysteresis loops in both compression and tension loadings. In 1987, Bergman and Goel introduced hourglass shape or ADAS yielding steel plates as flexural energy dissipators. In 1993, Tsai et al. Proposed the triangular shape or TADAS dampers as an improved version of ADAS. In 2006, Chen et al. Proposed the use of yield shear panels for passive energy dissipation. In 2010, Maleki and Bagheri introduced a new type of damper consisting of a single pipe called pipe damper. Their experiments showed adequate ductility, however the dampers demonstrated little stiffness and proved low ultimate force capacity. There are various types of dampers introduced in the industry, such as metallic damper, viscous dampers, and friction dampers. Metallic dampers have low post-elastic stiffness, but the viscose and friction dampers have zero post-elastic stiffness. The metallic dampers can be categorized in three groups. The flexural dampers, as in ADAS or TADAS systems. Shear dampers, the link beams in EBF systems and vertical shear link and a steel plate shear wall are examples of these shear dampers. And also uniaxial dampers, which the buckling restraint braces, BRBs, are the most famous instances of these dampers. There are many practical applications of dampers in buildings, such as the first BRB application in Japan in Nippon Steel Structure number 2 in Tokyo 1987. Also, another application of dampers, which is a viscose one, in Tohoku Institute of Technology located in Sendai, Japan, constructed in 2003. An instance of application of viscose damper is the Torre Mayer Tower in Mexico with 57 stories, a tower constructed with steel and reinforced concrete material. Another application of viscose damper is the Riemann bridge in Greece. A unique application of friction dampers in high-rise buildings is TCI Tower, located in Tehran, Iran. This building is located in the high seismic risk zone of Tehran. The tower has 36 stories and total height of 116 meters from the footing. The main lateral resisting system of the tower is SMRF in two directions, and the friction dampers are added to the main lateral system to improve the seismic performance of the tower during strong ground motions. A total of 170 friction dampers with capacity of 800, 500, 400 kilonewtons are applied. The details of the dampers are shown in the photos on the right hand. An innovative type of metallic damper called scorpion yielding connector or brush type damper is applied in Alden Art Museum Foundation in British Columbia. Introduction of Elastomeric-Steel caution damper. In this slide, the hysteresis curve resulted from the cyclic loading of steel caution is displayed. As can be seen, the behavior of caution is more appropriate in shear in comparison to tension compression. Also, the cyclic performance of the elastomeric bearing was investigated by Khaloo et al. In last year. The results show linear elastic behavior of elastomeric bearings. The proposed damper in this paper is a combination of steel caution and elastomeric bearings. The steel caution in shear provides an excellent energy dissipation for the new damper, while the elastomeric bearing provides constant lateral restraint and stiffness, especially in the post-yield zone of the steel caution. This way, the new proposed damper can be a combination of the benefits of steel and elastomer. Cyclic assessment of ESC damper. As can be seen in this slide, the ESC damper is composed of two back-to-back channels. One end of the channel is connected to the brace connection, i.e. gusset plate, while the other end is free. A T-section is located in the middle of the channel. The T-section is connected to the channel from one side and the elastomer and caution in another side. This way, the caution and elastomers are loaded in shear. The section of different parts of the proposed damper is shown in below, and also the application of the damper in the brace assembly is depicted on the right. The ESC damper is composed of two materials, namely steel and natural rubber. The steel is composed of ST37 according to the DIN standard, with the yield strength and ultimate tensile strength of 235 MPa and 365 MPa, and the ultimate strain of 25% was considered respectively. The hyperelastic material with Neo-Hookean strain energy formulation with the calibrated parameters shown in the top table is used for the rubber material. There is a good agreement between the numerical results and the experimental one based on the hysteresis curve shown in the slide. The loading protocol recommended by FEMA 461 was used for the applied cyclic loading. The first cycle was assumed to be capable of causing the ESC to yield. The next cycles were then multiplied by 1.4 10 consecutive times. Each of the cycles must be repeated twice, meaning that a total of 20 cycles are applied to the device. To calculate the yielding displacement and force of the damper, closed-form formulation derived by Moeini et al. Were used. Now, the analysis is conducted using Abacus software. The cyclic response of the finite element model is shown in this slide. The left figure shows the hysteresis loops. The vertical axis is force and the horizontal axis is displacement. The ESC hysteresis loop is wide and symmetric with good post-elastic stiffness. There is no degradation in stiffness and strength of the damper. The middle figure is the effective stiffness extracted in each cycle. As can be seen, there is a constant stiffness after displacement of 20 millimeters. The equivalent damping is calculated for each displacement cycle on the figure on the right. There is a high average equivalent damping in the ESC damper. The main conclusions of this study can be summarized as follows. The proposed device is made of common materials, and the production is not costly and hard to achieve. The post-elastic stiffness of the ESC damper is proved to provide over strength of the brace and the overall structure. The elastomeric pads do not possess much covalent damping, thus the yield capacity and elastic stiffness of the ESC damper is unaffected, indicating that the demand of the structure will not be affected. The effective stiffness of ESC dampers tend to converge to a constant value after certain displacement, unlike the other dampers. And finally, the ESC dampers showed an average equivalent damping of approximately 27%. I tried my best to summarize the presentation in the time limit considered by the conference. More details about the ESC damper is found in the article in the proceeding, with the title mentioned in the bottom line. I would be happy to answer any question or discussion via the email noted in this slide and the QA session after the presentation. Thank you for your attention.